Hi everyone, I'm really excited to be with you today and to get to talk with you about relationships. Not those kinds of relationships, but relationships between variables. Because I think this is where everybody's brain goes. This is what we're all excited about. And this is the launching off point for all kinds of predictive analytics and also program or policy evaluation. So most of what we want to do with our data has to do with understanding and evaluating and modeling relationships. And lots of the fun is in getting to choose the appropriate model and execute it and discover new and interesting things about those relationships. And today we get to start with the simplest and I think in some ways the sort of workhorse model that I personally always come back to. No matter what sophisticated model I plan to employ or think I need to employ, I always run a linear regression first. It's easy. No one needs to be like, I had this colleague in graduate school. We would have these weekly meetings with all the other graduate students with the same advisor, and we would all get together and we would talk about our plans and our things. And he wouldn't run anything on the computer until it was already like set in stone that this is what he was going to report out, which on some level, I suppose, is nice, but on the other hand, computers make it very easy for you to run all kinds of things. And so I think the thing that we're going to learn about today and talk about today is something that I hope you find useful across sort of many applications that you have in doing data analytics. So let's begin. Let's start with a review of statistics and an example. Today we're going to take a look at 100 flight squadrons. Each experiences unscheduled maintenance actions. We're going to call them UMAs for short. Each UMA costs $1,000 to repair on average. We have a well-constructed random sample on the number of UMAs in 36 squadrons during 1 year. It looks something like this. So we have some number of maintenance actions, right? We can take the overall average and the standard deviation. So if we want to predict the cost of unscheduled maintenance actions to the Navy, we would want to, use that average number of unscheduled maintenance actions, and we would go to our handy dandy normal distribution, label that mean of 60. We're wanting to know how many we would have on average, so we would use our standard error to map it to our normal distribution and get a 95% confidence interval. We expect to have 60 plus or minus, 2 times about 2.08 or 55.98, so about 56 to 64 unscheduled maintenance actions per squadron per year on average. All right. And that makes me happy, right? I've used my statistics. I've employed what I know about normal distributions to make a prediction. Little did you know you could do that, right? Based on historical data. Great. And sometimes that's all you can do. That's the data you have. It's the best you can do, and sometimes it's good enough. But sometimes what you want to understand is some of the underlying relationships that would drive something like these unplanned maintenance actions. So a couple of things we might expect could drive those could be inexperienced pilots. If a base suddenly is populated by inexperienced pilots, does that lead to more unplanned maintenance? Arguably, flying more could also lead to more unplanned maintenance. And understanding these relationships could help make our predictions better, because perhaps that snapshot of the past isn't as good a prediction of the future because of changing relationships. So if, for example, we suddenly want to fly a whole bunch more on the same aircraft, well, that could have an impact on these UMAs. If we get a whole bunch of more experienced pilots or less experienced pilots, could that have an impact on the unplanned maintenance actions in the future? So understanding what variables could influence those things and how we can model that is key to sort of making these predictions powerful under changing circumstances. And so today we're going to take a look at a foundation for answering financial and resources management questions by examining and describing simple relationships using two variables, correlation and simple linear regression, to provide information to help answer a question. We're going to provide the language and basic concepts to support the analysis of more complex resource questions. So while we're going to start here today, we're going to build on this simple model and make it more complex moving forward so that we can model things more accurately and answer more complicated questions. So let's start with describing the relationship. Is there a relationship? Might be the first thing we want to know. So what we want to know is, do the two variables move together? Is there some evidence that these two things are related to each other? I have lots of hypotheses. I've run around running lots of regressions in my life, and sometimes things are related that you expect to be related, and sometimes they aren't, right? And we might also want to know what kind of relationship they have. Is it a positive or a negative one? Do they move in the same direction or in the opposite direction? We also want some sort of sense of how strong the relationship is. Two things can be related, but there can be a lot of noise in the relationship. Two things can be related, right, very closely and strongly and move together, right, almost perfectly. So we want to ask questions like, how closely do they move together? All right. So a correlation coefficient is a statistical measure of how closely two variables are moving together in a coordinated fashion. And it's a starting point for measuring the relationship. It measures both strength and direction, so we can have positive and negative correlations. And its value ranges from -1, a perfect negative correlation, to +1, a perfect positive correlation. Notably, correlation coefficients are going to give us a sense of linear relationships. We can have nonlinear relationships. These aren't going to show up with any kind of correlation. So we can have perfect nonlinear relationships, and you may still get a correlation coefficient of 0. But generally, 0 indicates no linear relationship between the two variables. Here's the formula. I expect, you to memorize this by next week. Ha ha ha, just kidding, right? It's very easy to ask the computer to do this for you. You can ask Excel, R, it will give you the correlation coefficient of some X and Y variables. We also might want to plot a scatter diagram. This is good for helping you figure out if there's something nonlinear, right? And to verify that the relationship appears to be linear, and kind of gives you a sense of how related the variables are to each other. Sometimes when we have a lot of data, this can be too noisy to see, and sometimes when we have other sort of confounding variables, this can be too noisy. So plotting a scatter diagram isn't a perfect solution, but I have to say, I used to be way too lazy to do this, or way too much. I want to jump into code. I want to get the model. I want to do the complex analysis. And I would skip things as simple as scatter diagrams. And now I make lots and lots of scatter diagrams because it helps me do better analysis. It helps me see weird stuff in my data, outliers, strange behavior. We're not trying to make beautiful graphs to necessarily show the boss here, but we're trying to take a look at our data and understand what's going on. So you can see groupings, you can see patterns, you can see typos sometimes when you go ahead and start with a scatter diagram. But at the very least, and perhaps most importantly, we can kind of start to see, do things look related, and does that relationship look linear? So in a perfect world, we'd see something like this, a strong positive correlation. This is R is equal to 1. So a perfect positive correlation. And we could see a perfect negative correlation. Here you have R is equal to -1. Note, we don't know anything about the slope from our correlation coefficient. We're going to need our linear regression model to get to slopes, but we do know something about the strength of those relationships. Here, we have a positive correlation, but it's not quite perfect. It's going to give you something like R is 0.7, which is still a pretty strong positive relationship. I like to think of this as things like, this is what happens in the real world, right? Sometimes you can be like my friend who drives her car. I mean, yes, it's a Toyota, so they're pretty reliable, but didn't know you were supposed to change the oil and drove her car for hundreds of, well, maybe tens of 10,000 miles, 20,000 miles without ever figuring out she needed to change the oil, right? So sometimes you drive your car more and it breaks more. Sometimes you drive your car more and you get lucky and it doesn't break. But generally, the more you drive your car, the more it's going to break. And that's what these kinds of relationships tell us. Yes, there's a relationship. It's not perfect. I can't predict that your car's going to break next Tuesday based on the number of miles you've driven. But I can predict that it's more likely to break down soon because of the number of miles you've driven. Similarly, we can have these kinds of negative correlations where you have strong, but not so strong a perfect relationship. And then you can have what we like to call a shotgun blast, which we would say is no correlation between these variables. R here, 0. You can also spot sometimes some nonlinear relationships. These crop up in things. There are some things that get better for a while and then worse, or worse for a while and then better. You're going to see it in the rental price data. I'll give you a hint, right? In the rental price data, when we look ahead to our multivariate models, is that age of properties. I live in a town where there's all these beautiful Victorian homes. There's also some sort of, like 1970s homes. For a while, houses, as they get older, the price starts to go down, right? Because they just get crappier and they need work and it's kind of boring and kind of dated looking. And then at some point, things become historical and they have value because they're historical. So instead of losing value as they get older, they essentially gain value as they get older. So you can get some of these kinds of funny relationships in data. And we'll see them in financial management data. We'll see some logarithms. Not going to dwell on it too much here. We'll talk about those relationships in particular and how we model them later. But certainly there are nonlinear relationships in data that are important, and we're going to revisit those later on. So, does the pilot experience rating predict UMAs very well? Looking kind of like a shotgun blast there. What about sorties flown? Do those predict UMAs well? That looks like a much tighter prediction. You can see it in the correlation matrix. If we take a look, I would go over to the far right column to UMAs. If you take a look at the pilot experience rating, you have a correlation coefficient of about 0.24. It's something, it's related, and it's a positive relationship. More experience is more UMAs. Kind of odd. Sorties flown is a positive relationship, and it's a much stronger positive relationship at 0.98. One of my pilot students told me he didn't think it was surprising that more experienced pilots caused more unplanned maintenance actions. But at any rate, he thought that relationship should be stronger. This data doesn't bear it out. We could always go and gather more data. Anyway, a word of caution here is that we often we love to do inference, right? We love to figure out what is the data telling us and jump to conclusions about causality. I see this all the time with students. They jump through all of these hoops to prove that, okay, because this and this are related to each other, one thing must be causing the other thing. Correlation measures the coordinated movement of two variables. It's also not going to matter when we call one x the independent variable and one y the dependent variable. That's not going to magically change anything to where causality, where we're proving causality. When we have these relationships, whether it be in linear regressions or with correlation coefficients, we're proving a relationship that exists in the data. We're not proving what drives what, or whether there's some undisclosed additional factor that's driving things. We're simply seeing that there's coordinated movement of two variables. So let's have a little fun. Variation in two variables may be due to a third common variable, as we said, or it could even be due to chance alone. So here's some fun ones. ice cream and murders. Clearly more ice cream and more murder, right? So is it that the sugar high lends itself towards making people feel violent? Maybe the come down from the sugar is making people feel violent, or it's some bizarre No, well, this one is a third factor that's missing from the graph here and from the story, is that there's more murder in May, June, and July. So it seems that perhaps hot weather lends itself to more ice cream consumption and more murder, which is a weird story too. But, for the moment, this third hidden factor there. Here's a fun one. Fresh lemon imports lower U.S. highway fatalities? No idea. Facebook caused the Greek financial crisis? Fun, but most likely, right, other things are driving both of those things up. Both Greek debt and number of Facebook users happen to both be going up over time. You'll see a lot of these in time series data, especially in sort of one trend direction time series data. You'll see a lot of these kinds of spurious correlations. And it's driven a lot of bad policy. So yes, it seems very obvious to me, to you, that of course the number of Facebook users has gone up over time. Fine. And that Greece started to get into trouble in that period from 2005 to 2011. And if you looked outside that period, maybe it wouldn't be such an interesting story. And okay, so they both went up over time. Big deal. But people use this all the time to weave these fantastic tales about how, right, Facebook caused the Greek financial crisis. It's a great headline. It's just bad data analysis. Facebook also canceled out the cholesterol-lowering effects of Justin Bieber. Huh? Right? Even crazier. Here's some of the most bizarre correlations out there. One of my favorite ones doesn't get on here, but there's a correlation between mozzarella consumption and engineering degrees. And having Italian parents-in-law, I'm sure they believe that mozzarella would improve your ability to excel in an engineering program. But there's all kinds of wacky ones. Ice cream consumption and murder, a pirate shortage caused global warming, living in a poor country increases penis size, eating organic food causes autism, M. Night Shyamalan makes bad movies because people don't buy newspapers, using Internet Explorer leads to murder, Mexican lemon imports prevent highway deaths, obesity caused the debt bubble, Facebook caused the Greek debt crisis, and Facebook also canceled out the cholesterol-lowering effects of Justin Bieber. I mean, that last one's kind of my favorite, right? Because you see the decrease and you see the increase and you go, okay, it must be causal, right? Wrong. All right. So once we've kind of determined that we see some kind of relationship from a kind of preliminary look at the data, we might want to use that information and get a model of it. So we might want to try the simple linear model. Here it is. We're going to put it in Greek letters just to be fancy. This is the equation for a line that you met back in middle school. Y is equal to, right, so y equals mx plus b. We've just reversed it here. We've put the b at the beginning, beta naught, and we've made the m beta 1 and your slope as your slope coefficient. Here we can talk about x in a bunch of different ways. We can call it the predictor, the explanatory, or independent variable. For a lot of predictive analytics, we'll call it the predictor. I often call it the explanatory or independent variables and use all of these terms pretty much independently. I've been trying to get in the habit of calling y the response variable, again, from being in predictive analytics land. But I'm used to calling it the dependent variable, often the outcome variable. Here, B0 and B1 are model parameters we estimate. So when we talk about parametric and non-parametric models, here we're estimating parameters. It's a parametric model. Linear means the relationship between the dependent and the independent variable can be expressed as a straight line. So we're going to use, right, a linear or straight line kind of model to fit the data. Here, for the conversation, for the example we've been having, we're going to make UMAs our dependent variable, and that's going to be a function of our independent variable, sorties. We're going to go ahead and formulate the model, putting it in terms of UMAs as our y variable and sorties as our x variable. And then we're going to use the computer to estimate the intercept and the slope. I had a statistics professor that made us learn like the actual formulas for doing this. I have a colleague who once upon a time had to estimate these by hand. My statistics professor made us, do proofs to prove that the estimators from the least squares line was the best linear unbiased estimator under certain assumptions, and when the assumptions were violated, it was no longer the best linear unbiased estimator. And we'll talk a little bit about what an unbiased estimator means and what an efficient estimator is. But for the most part, I'm not going to make you do that stuff. We're going to use the computer, and we're going to talk about some problems that crop up in these models, which have to do with the underlying assumptions in math and the things we need to be aware of and test for and make corrections for. But we don't necessarily need to dive into all of the underlying statistics in them. All right, so we gather some summary statistics about sorties flown and unplanned maintenance actions. We see there's some variation in both of them, which is a good starting point. Minimums and maximums kind of make sense, nothing too wacky. Always good to take a look, right? You wouldn't want the average to be 134 and the maximum to be 196,000. But this all looks within sort of something fairly kind of normal ranges. So we had our scatter plot, and essentially what we're going to do is we're going to go and fit a line to this scatter plot. The computer is going to fit the line that best connects these points. You'll see here that the orange line does a much better job than the blue line, right? There are other lines it could fit, but they won't as closely cluster, the points won't so closely cluster around those other lines. So it's picking the line where everything is the most clustered it can be. Technically, what it's doing is it's taking all of the differences between the line and the points and minimizing the square of those differences. So it squares all of those little green bits, which we call residuals. It squares them all to do two things, to take away the influence of positives and negatives. But we could just take the absolute value. What we also want to do is punish really far away things. So it says anything that's being too way far away, we need to kind of pivot towards it to reduce those, reduce that sum of squared errors. So that's what it would be. It's the sum of the difference between the predicted y, which is what the line gives you, are the predicted values. So at any given x, the line gives you a predicted y, and there's some real y's. So it's the difference between all the real y values and the predicted y values. All right, so we have our formula for a regression line. This is our estimated linear relationship. It includes, right, so we put hats on things when they're estimates. So y hat is the estimate of y. Beta naught hat is the estimate of beta naught, or the intercept. Beta 1 hat is the estimate of our first slope coefficient, or our slope coefficient here. And little epsilon is the error. It's unobservable, but it can be estimated. We're going to estimate it with our residuals. And it gives, and it's important statistically in the model. So all things have some kind of error, and we don't know it exactly. But we need to be able to assume some things about our error. It needs to be a normally distributed random variable with mean of 0, variance, right, of sigma squared, and ultimately to be supported by the central limit theorem and to allow us to use the estimates properly from our regression. We're going to talk later about what happens when those errors aren't behaving the way they should, and some weird behavior we get from them, and some corrections that we make because of it. Now, when I first started a job as a cost estimator, I went to work with someone who, to my horror, suggested that we should always suppress the intercept, get rid of beta naught, just make it equal to 0. So our intercept tends to take up a lot of the slack of our model. It takes up a lot of the error. And you see here with that red line where the line was fitted without an intercept, without a constant, without beta naught, that line just doesn't fit as well. So allowing the computer to fit both beta naught and our slope coefficient makes a lot of sense for getting a good, well-behaved fitted line. All right, so here's some output from R when we run our linear model. And this is a little linear model of our UMAs over sorties. There's a lot of output here. We're going to talk about what it means and what's useful to you and how you can use it to make good predictions and evaluate the value of this model. So first and foremost, we can use this model to help us fill in that equation. So we had our general form of our equation. We can fill that in with these coefficients. So the intercept is that intercept, negative 6.36, and our slope coefficient is 0.492. So you can put it into your equation, and then you can use that equation to estimate from, if I have 100 sorties, how many unplanned maintenance actions am I going to have? So it allows us to essentially put our own estimates on this model. And it can help us realize that an extra sortie leads to about 0.49 extra unplanned maintenance actions, which is also a really handy thing that we can learn from this. And we can use the equation very directly to plug in 100 sorties tends to lead to about 42.8 unplanned maintenance actions. We're plugging in those numbers to get those answers. There's no computer mystery magic here, right? These are just giving us the information fairly directly. So what else might we want to know? Well, we're going to want to take a look at our model to figure out how well does the model explain the variation in the dependent variable, and how confident are you in the prediction? Does the independent variable sorties really seem to matter? And is the interceptor constant also, we might check to see if it's statistically significant. Though I don't tend to get rid of them even if they aren't. So how well does the model explain the variation in the dependent variable? We tend to go to a measure called R squared, which is the fraction of the total variation in Y that is explained by the regression. So it varies from 0 to 1, 1 being a very, everything is explained, which actually means it's a problem. But here we have an adjusted R squared down here at the bottom of our output of 0.952. So it's suggesting that about 95% of the variation in unplanned maintenance actions is explained by sorties flown, which is a really absurdly high adjusted R squared. We'll see R squareds like that when we do time series analysis, but you don't always see something so high. But big numbers are generally better here. And the bigger that is, the more confident we're explaining variation. We also look to the standard errors of our estimates. We can use those, we're going to use them in a minute, to build a confidence interval for our estimate. And here, just like smaller standard errors are better when we were doing regular old hypothesis testing, smaller standard errors here are better as well. So our model has its own standard error. There at the bottom, 2.639. And so that's going to be the sort of standard error that we're going to build confidence intervals of our prediction. You can see the confidence interval here with the gray band around our estimate. Interestingly, the farther you are from the mean, the less confident you are in the model. So the model tends to do its best job of predicting right in the middle around the average number of sorties flown. It'll predict about the average number of unplanned maintenance actions. So around that point, we're really confident in our model's ability to predict. The farther we get away from that, we tend to have fewer data points to predict off of, and that drives us to be less confident in the predictions of our model and give us a wider band for the confidence of our model. We also might want to estimate something we will call a prediction interval. So just like we estimated our predictions, we might want to know, well, how reasonable, how likely is that prediction? What's a good confidence interval for our prediction? People love point estimates. They love to take a model and estimate, okay, well, here's the estimate that comes from my model. But just well, how confident were you that the true average was 50? How confident are you that the next repair will take between 70 and 90 minutes? We want some kind of range for our estimates. And while our confidence interval gives us a range for the average, or kind of a range for that on average, if you fly 175 sorties, you will have on average between the lower part of that and the upper part of that gray band. We would expect that 95% of the observations of unplanned maintenance actions will fall between those dotted gray lines. So just like we have wider confidence intervals for our point estimates than we did once we got to standard errors when we're talking about means, that's essentially what we're doing here with a prediction interval vice a confidence interval. So it's an important distinction, and fortunately, R can calculate both for you. Calculating prediction intervals is kind of a pain. You can calculate a confidence interval as 2 standard errors looking at your regression output. Prediction intervals are a little trickier, but we can use the computer to do that as well. So the final thing we might want to do to evaluate the quality of our model here is we want to know, do sorties really seem to matter? And so if sorties do not help to predict unplanned maintenance actions, we expect that the slope is equal to 0, so a flat line, right? So basically that means that at any value of sorties, you expect about the same amount of unplanned maintenance actions, a flat, straight, horizontal line, which has a slope of 0. So beta 1 would be equal to 0. If it's not equal to 0, and almost always the computer gives you something that isn't exactly 0, is it far enough away from 0 for us to believe it's different than 0, right? So here, our null hypothesis is essentially that beta 1 is equal to 0, like we had our null hypothesis about our other hypothesis tests. And if it's not 0, is it far enough away? Do we have sufficient evidence to prove that it's not equal to 0? So going back to our regression output, we have some measures here to help us evaluate how high a quality of evidence we have. So we get standard errors. You've seen standard errors before. And so you'd want, you can build a 95% confidence interval for your estimate for your coefficient with the sort of plus or minus 2 standard errors. The computer essentially does that for you, and it gives you the p-value and a t statistic and a p-value that help you do this. So we're looking for a t-value roughly, this is like your z-score that you've seen before. So plus or minus 2 t is going to be, so a t of 2 is going to be roughly sufficient evidence. T's much bigger than 2 are better. T's that are smaller than 2 mean we don't tend to have sufficient evidence to reject the null hypothesis. The p-value tells you how sufficient that evidence is. So teeny tiny p-values are good. Anything less than 0.05 means it's just like what we were getting from our p-norm when we were doing that before. So anything less than 0.05 is better than 5%, or less than a 5% chance that this is equal to 0 here. And for sorties flown, if you look here, that 2e to the negative 16 is a teeny tiny number. That means 0.0000000 blah 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 zeros, lots of zeros, 15 zeros. So it's a 0, 15 of them 2 is that e to the negative 16. You scoot that over the negative direction. So that means that's a teeny tiny number. So it's a teeny tiny chance that this value came from, exists despite the fact that the real value is 0. right? So this is the probability of getting this estimate if the real value is 0, is the technical definition of that p-value. And so this means there's a very small chance that the real value is actually 0, which is a good thing. It means that we have some confidence that sorties flown are a statistically significant determinant of UMAs. So there's some caveats. There's always lots of caveats, right? These are the things we all just want to ignore and do data analytics and ignore all the caveats, because doesn't big data solve all the problems, right? Okay, in one case it does. Larger is better. You're going to have more accurate estimates the larger the sample size. Also, it's important to have a range of X values. I like to use as an example here, if I want to know, right, the impact of, right, being male or female on educational attainment. If I have a data set of all men, I can't find out very much about the differences between men and women, right? So, similarly, I need a range of X values. I need a bunch of different numbers of sorties flown, or I can't tell how much, right, the number of sorties flown influences unplanned maintenance actions. If everybody flies 150 sorties, I don't have any information that would help me use the sorties to predict unplanned maintenance actions. It might be that if everybody switched to 100, it would wildly affect unplanned maintenance actions, but I won't know because everybody's flying 150, right? I need some variation to know something about how X affects Y. And so having a broader range of X values is helpful. Also, having smaller errors makes for more accurate estimates. There's not a whole lot you can do about this. Besides, later we're going to talk about adding explanatory variables. But some data is noisy. Some kinds of relationships are messy. I study when civil wars start. Well, there are some things that influence when civil wars happen, but the exact date that one is going to start, that's a messy thing to try to predict. And it's going to have bigger standard deviations in the error terms. The smaller those standard deviations, the more accurate our estimates can be. So for some things, there are nice and tight relationships. Other things, big messy relationships. And we'll want to think about that as well. So there's always more. I always like to say, if this is too easy, don't worry, we'll make it more complicated. And if I don't make it complicated enough, fast enough, let me know and we'll work on that too. So here we go. We're going to move on to adding more variables to our linear model next week and adding a sophisticated array of types of variables to our model. So those nonlinearities, we don't have to run away from our linear model just yet. We're going to find some ways to incorporate some fairly sophisticated things in a simple linear model, in the general linear model. There's also a whole bunch of things that might go wrong, and we're going to start to work on these, like using linear regressions for nonlinear relationships without modeling it correctly. Use your scatter diagrams to avoid that. We've talked about avoiding that correlation and causation are the same thing, but the deeper you go down this modeling rabbit hole, the easier it is to forget that. So don't. Leaving out variables that matter. This is part of the motivation for why we're going to use these bigger, better models with more variables included and include multiple variables in the same model later. And we're going to talk about how to do that and the sort of pernicious effects of omitted variable bias. And we'll talk about program evaluation and attempts to really dig into and solve these omitted variable bias problems. We're going to talk about extrapolating beyond the data or predicting too far outside of its known range. It's no good to take our sorties data and try to predict what would happen if we flew 100,000 sorties when everybody's been flying, between 75 and 200, right? It's just so far outside the scope of what we've been doing that our project here isn't going to be very useful at making those predictions. And this happens all the time. Well, we've been building all of these 1,000 square foot buildings. What would it cost to build a 100,000 square foot building? Way different ball game. You can't use one to predict the other very well. You can use it. The model will give you an answer, but it probably won't give you a good one. We're going to do some data mining later in probably in the next course and talk about using the computer and using machine learning to help us choose variables, but there are some problems with this approach too. And I like the quote, "If you torture the data long enough, it will confess." I suppose after this course, you'll be better at lying with data. And constantly trying to make the model say what you want it to say, even when it's not, is a kind of way we get about lying with data. We have to be careful. If our predictor variables are too highly correlated, we get technical problems in our models. And also, people get excited about, well, I should be using the latest machine learning technique. But that's not always, I need to be using a non-parametric model. Not even all of those are that fancy, but that to say, you don't necessarily have to go there. I like to start with simple things and make justifications and reasons for why we want to choose something more sophisticated. There are often reasons to keep with simple, straightforward analysis. Primarily, in my view, because people can understand it, and communicating and telling stories with our data is an important part of what we need to do effective analysis, right? We need to convince somebody it's worthwhile. And that's easier, I think, with more straightforward analysis. Unless you're just really good at building these black boxes of more sophisticated models and convincing someone that it's something they need and something that they should pay millions of dollars for. I suppose that's why I'm sitting here not doing that kind of work right now. But that's okay. I'd rather do honest work that gets us better results, and I hope you would too. And I think sometimes starting with simple things and using simple things where they're appropriate is a good place to begin to use data analytics to make better decisions. So I leave you, I think, on a hopeful note here. George Box, a famous British statistician, once said, all models are wrong and some are useful. So we're going to dig into and use lots and lots of wrong models in this course, and hopefully amidst them all, find some really useful ones and find some that help us understand the world better, make better decisions, and do good work with data. So with that, I look forward to walking through how to do some of this work in R with you and exploring lots of simple regression models in the near future. Thanks.